Okay, so learning intention, what the term scale factor is and how it applies to shape. And once we've got that, if you're able to remember the term scale factor and solve problem using it, then we should be okay. So before we can even start, what are the conditions for similarity? So when you are given two shapes, the definition in math to say that the two shapes are similar if we've got what we call sides that are proportionate in size and angles that are equal. Okay, so if I look into this, I'm thinking all these rectangles are not similar, even if they are rectangle, to one another, because they do have the same angles internally. So you can see 90-degree, but the sides are not equally proportionate. So if you've got that side here, you can see this is doubling that side, but because we've not doubled that side, they're not proportionate. So we can't say they are similar. And it's the same for that one. You've got probably 1, 2, 3 times that side, but not the breadth there. So let's have a look at other shapes when we do have similarity. So in this example here, I've got a couple of rectangles. Can I say they're similar? Yes, because I can see that I've got the same angles on each corners. All angles are 90-degree. And if I look at that side, which is 8 centimeter, to get 16, I've doubled it. And if I've got 5 centimeter on that side, and to get 10 here, I need to double it. So both sides now are proportionate. And we can clearly say here that A and B are similar rectangles. So the question we might get asked is, find the scale factor of enlargement that maps A to B. So we went from 8 to 16. So we've enlarged 8 by a factor of 2. And we went from the same scale factor. From 5, we went to 10 by enlarging it by a factor of 2. So that's what they called the enlargement scale factor. And if we were asked to find the reducing scale factor, it'd be the opposite of timing by 2, which is divide by 2, which is what we call a half. Okay, so that is what we mean by scale factor. So now let's have a look at this example, because scale factors would apply to any shapes that are mathematically similar. So the first thing we said was looking at angles. So I've got the red angle here that correspond to that one, the yellow, the beige there, and the black. So all angles are the same. And do I have a proportion here? So I've got a 3 centimeter for that longer side, and I've got 15 centimeter for that longer side. So I went from 3 to 15 by a factor of time by, how many did I time 3 to get 15?
5.
Time by 5, so I get 15. So the 1.4 here, I can quickly check that the scale factor is the same. So if I do 5 times 1.4, 5 times 4 is 20, so 0 reminded 2. So 5 times 1 plus 2 is 7. So that works okay. So I can see that my enlargement scaling factor, which we call ESF, is 5. So now, given that the shapes are similar, the type of question you may get asked during a Nat 5 exam is find the value of y and z. So to find the value of y, like I just said, we went from 3 to 15 by a factor of 5. So to find y, we just need to apply that same scale factor to that length here, which is 2. So 2 times 5, then that would mean y equal 5 times 2?
10.
10. So the scale factor is 15 divided by 3, which is what we found, 5. So y is just 2 times 5, which is 10. Now, the reducing factor this time, so we're going to call it RSF for reducing, is the opposite of timing by 5, which is dividing by 5, 1/5. Yeah? Or I could have just said 3 divided by 15 if you wanted to. It's the same thing. So 1 divided by 5 is the same as 3 divided by 15. But because you've got an equivalent fraction in its simplest form, the fraction is 1/5, 0.2. So Z is 0.2 times 6, which is 1.2. So we've looked at both enlarging scaling factor and reducing scaling factors, and we've applied them in order to find the sides, okay? So sometime what they'll do is they're going to give you the two shapes, but have you noticed they've not put the shapes exactly in the same orientation? But because we can see that the angles are the same, I'm going to pick a couple of sides that are just to check. So between the red and the yellow angle, I've got 10 and I've got 4. So the reducing factor would be 4 divided by 10 or 2/5. Okay, so to find A, I need to find a reducing scaling factor first. So the first thing we do is we find the exact same side on the other side. So 4 divided by 10. And what you need to keep as a hint, whenever you're going to get a reducing factor, the value that you would get is always less than 1. Because you're reducing, you're going to time by a number less than 1 in order to get a smaller number. So that's 0.4. Now to find A, I'm going to find the length which is between those two angles there, 8, and I'm going to time it by the reducing scaling factor. So 8 times 0.4 is 3.2. So I've got A equals 3.2 centimeter. So that would be my first answer for A. And to find B, this time we're going to look for the opposite of reducing, enlargement scaling factor, which is the opposite of 4 divided by 10 is 10 divided by 4, or 5/2, 2.5. 10 divided by 4, which is 2.5. So to find B, I'm going to find the length that is associated with B on the smaller scaling shape. So 2, I need to do 2 times 2.5, and that should be 5. So B equals 5 centimeter. So I've given both answers, A and B. One using a reducing scaling factor and the other one enlargement scaling factor. And I can quickly see that A 3.2, that would make sense. And B 5 centimeter, if I've got 7.5 here, yeah, that looks okay. Usually they're not exactly to scale, but we can quickly give a check. So in this exercise, I've been asked to find the scale factor for each. So I went from 5 to 10. So you would just write here ESF because we're enlarging. ESF equal 10 divided by 5, or just 2, right? We've just double it. So the longest side divided by the smallest side, and that is 2. Now to find a question mark, it's just 2 times 9. So enlarging scaling factor times 9, and that is 18. So if you were to use models, for example, where you've got to make a shape of some sort in a bigger scale, then you can just use that technique. Let's say you work with houses and you want to make a smaller version of a house. For example, in this case, I've got an enlargement here, 10 meter to 50 centimeter. So the thing about scaling factor as well, I forgot to say, you need to use the same unit in order to give your scaling factor properly. Okay, so for B, I've got millimeter, millimeter, so that's okay. You can easily see, oops. You've got an enlargement here, ESF is 140 divided by 40 because they're similar shape, and 140 and 40 are corresponding side. So if this is a calculator, it's quite straightforward. If this is not a calculator, you just go divide by 10 or 7 divided by 2 because you divide by 2. So you time by 7 and you divide by 2. That is the same as 3.5. Yeah. So if you got a question like this, no calculator, it's better to keep the fraction, because this here is 22 times your scaling factor, 7 divided by 2. So if I had gone and just put 3.5, 3.5 times 22 is hard, whereas 22 divided by 2, that's 11. What's 11 times 7?
7.
77. So do you see why
Margin scale factor, yes. Yeah.
keeping fractions is always better than using decimals? Because it's much easier to simplify. Okay.
Is it non? That could be non-calc though.
Yeah, so this could be a non-calculator question.
Get into habit of
Keep
basics without using a calculator then.
Yeah.
Yeah.
So that would be a typical question where it's non-calculator, for example.
Okay.
You would still get the answer if you do 3.5 times your 22, but you've got more chance to make a mistake
True.
than doing 11 times 7.
Mm-hmm.
Okay. So same for C here. We've got 1.2 divided by 0.8, which is 3 over 2. So you can keep 3 over 2, and then 3 over 2 times 0.3, and it's 9 over 20, which is 0.45. And this is the tricky bit where you're asked to go from a 50 centimeter, 75 centimeter house, and they tell you that the real length is going to be 10 meter. So that could be an architect just trying to build to the correct ratio a house. So now enlargement scaling factor is where you need to be careful, because you need to change the 10 meter, for example, in centimeter, or the 50 centimeter in meter. So it's up to you. So 1 meter is 100 centimeter. 10 meter would just be 1000 centimeter.
that's quite a tricky because I hate exchanging units and it's a nasty one in that sense.
Yeah.
But
So then you can divide 1000 by 50.
Which is 500.
So what you do first, again, use your fraction knowledge, take away the zeros,
20.
and now what's 100 divided by 5?
20.
20, yeah. So that's your enlargement scaling factor. And to find the question mark, you just do 75 times 20.
1500 meters.
Yeah, so it'd be 1500 centimeter because we're doing in scaling in centimeter, and then you can just, yeah, that'd be 15 meter.
50, yeah, 15.
Yeah, so usually a house with windows at the top,
Just
double
realised
story.
as soon as I said 1500 meters, that would be the tallest house probably in ever lived in.
Yeah. So again, try and, if you give an answer, look at your answer and think, is that plausible? Because they would do it with plausible answers in them. Okay, so same for that car there. You need to change the centimeter into meters. That's how you would do that. Now, we're going to look at how the scale factor applies to similar triangles, because that, again, is the type of questions that you may get. So again, what we need to look at is to keep that ratio of each sides the same way we were looking at before. So angles needs to be the same. So you've got 70, 45. So that means that green has got to be 65. Yeah, it's got to be, because all angles in the triangles add up to 180 anyway. So these two triangles are similar since they are equiangular. If two triangles have two angles the same, they must be equiangular. Yeah. So once you've got two angles that are the same, because all angles add up to 180, the third angle's got to be the same. So you could be given a couple of triangles, and one with the bigger angles and one with a different angle. Find out the third angle straight away, and then you can say, yeah, now I can see they are similar because all three angles are the same. So again, we're going to use the same approach using scale factors. So if we go from a small to a bigger triangle, we'll look for enlargement scaling factors. So here it's going to be 12 divided by 8. So you just pick the bigger side divided by the smaller side, which is 1.5. Whereas the other way around, you can just take the enlargement scaling factor and just flip it around. So that'd be 2/3. So it's called the reducing scaling factor, 8/12. So you go from the small to the big one, and that's 2/3. Okay, so basically RSF is just 1 divided by ESF, or ESF is 1 divided by RSF if you want. So if you time ESF by RSF, you should always get 1. So find A given that ESF is 3. So if ESF is 3, you take the side and you time it by 3. So 3 times 9.
27. 27.
27, yeah. Now by finding the RSF, find the value of B. So we know that RSF is just 1/ESF. So it's the opposite of timing by 3, which is divide by 3. So 1/3.
5.
And then 15 divided by 3 would be 5. Okay? Or you need to do 5 divided by 15 to get 1/3. Same thing. So we know what the link is between ESF and RSF. That means we can work from one to the other. So let's see those couple of questions. So I've got a model made of a car on a ramp in a showroom. So we've been told that the ramps are similar. By calculating the ESF, find the height. So ESF, what I said was we go from big divided by small. So the two sides that are exactly the same is that long side here, 165 and 15. So you would just write ESF equal 115, 165 165 divided by 15. That is 11. So if I'm looking for H, now that I've got the scaling factor, so H is just 11 times 7, and that is 77 centimeter. Okay. So just use ESF times 7. That'd be us. So in this case here, I've got a reduction scale factor in order to find X. So we reduce from 10, we go down to 4. So here I'm going to have to find RSF. And we said that it's equal to 4 divided by 10, or 2/5 if you want. Now, X is just 17.5 times 2 divided by 5. That is 35. Is it? Yeah. Divide by 5. Yeah. 7 centimeter. Or X equals 7. Okay. Now let's have a look when we've got what we call parallel triangles. What do they mean by parallel triangles? So it's just as if you've got a smaller triangle embedded into a bigger triangle. So if BC is parallel to DE, then what we've got is two triangles, a small one and a bigger one there, and we call them similar because this angle here is the same as this angle, and this angle is the same as this angle when we use the F figure shape there. And that angle is always the same. Okay? So angle BAC equal angle DAE, and using corresponding angles with the F shape there, we can see that they're all equal. So a line drawn parallel to any sides of a triangle will always produce two similar triangles. So I've got DAE. Again, if I draw those, you'll see that they are similar. And if I was to draw again these two triangles, you'll see them similar triangles. Okay, so you can see how they build it up. So sometime you could be asked a question like this. We've got two triangles, similar, find the distance y. So the best thing to do here is split them up. Because y is the smaller side, then we would look for what we call RSF. So what I would suggest is draw the two triangles, the small one with 5 centimeter here, and the bigger triangle. You've got 5 plus 45, which is 50. So that's why it's better to draw them separately. Then you can see what the reducing scaling factor is, because you're looking for that side. We've got been given 20. So RSF is AE divided by AD, which is 5 divided by 50. And that is just 1/10. So basically you divide by 10. So if I'm given 20 centimeter here, I just divide by 10, the 20 centimeter. And y is just 1 times 20 divided by 10, which is just 2 centimeter. Okay, so for those who couldn't see it straight away, like I said, I would advise to just draw them two separate shapes and be able to see that. So this is a past paper question. Calculate the length CD. So I've been asked to find the length CD. So that's enlarging from 4.8. And after that, calculate the perimeter of the trapezium EBCD. So to do that, I've got a 10-meter triangle. So the scaling factor is 10 divided by 6, because the smaller triangle has got 6 here. 5/3. That's an enlarging scaling factor. So now I need to time 4.8 by this scaling factor of 5/3. That gives us 8 centimeter, or it should have been 8 meter. I'll fix that. And now I should be able to find my trapezium. I need to find that side first. So the scaling factor is 5/3. So AC is going to be 4.5 times 5/3, which is 7.5. So if I've got 7.5, that means BC is 3. So now you just add 3 plus 4.8 plus 4 plus 8. And that should give you everything you need to find 3.8 plus 4 plus 4.8 is 19.8 meters. Okay, so that's how you do that, by going step by step till you find everything you need from those two triangles. Okay, so sometimes what they'll do is they'll put a Z shape like this, for example, and they ask you to find the value of one side. And what you need to see straight away, that you've got what we call corresponding angles here, the red and the red, because of that Z shape, and the blue and the blue. So the best way to deal with these is, if you're asked to calculate an enlargement scaling factor, you need to find the sides that are proportionate to each other. And this time I've got 8 divided by 5. and then RT is just X, but you need to do, so it's going to be 4, that side there, times 8 divided by 5. So what I would say to my student is, every time I get something like this, so that you don't get confused, it's better to redraw them on your piece of paper as 2 separate triangles. And then you can say, okay, this is 8, this is 5, this is 4, this is X. So this is a typical question that comes quite often during exams with similar triangles. So with the parallel triangles, on Lecky, you've got 3 questions. So they're like individual questions usually. So you've got question 3, question 5, question 6. And it's page 241 and 242. Okay. So let's have a look what they look like. So as you can see, you've got the 2 type of embedded triangles inside each other, or one on top of each other, and then you can see that this angles is the same as this angle. So let's try C. We're going to try and do C. Calculate X. So I'm looking at this. I've been asked to calculate that long distance. So the first thing first, I'm going to put some markers so I know what angle is which. So I've got this angle there. A square angle. And it's this angle there. Corresponding angles. And it makes sense because here you've got the X shape and those 2 angles are the same. So in order to find X, I'm going to have to calculate this long distance. To do that, I've got a scaling factor here, 9/8. So if you were to draw from that point to there, you've got 9, and from that point to there, you've got 8. So your enlargement scaling factor, ESF, is 9/8. And in that same manner, RSF is just the opposite of 9/8, which is 8/9. So to find X, I'm going to find this distance first. So this distance is that distance times the ESF. So 9/8 times 7. And what I need to do is just add 7 to it. So 9 times 7, 63 divided by 8. 7.875 for this distance. And because we're looking for that total distance here, you get 7.875 plus 7, which is X. So X equal 14 0.875 meter. If we were asked to find this value here, then you would use your RSF. And that would have been 18 times 8 divided by 9. But they've not asked me that. And that would be 16 here. So if they had asked us to find that distance, you use the RSF. Okay. So the good thing about similarity is being able to figure out the length of a pole, for example. So Jack stands 3 meters from the base of a street lamp, which is 5 meters tall. The length of his shadow is 1 meter. How tall is Jake? So you could, if you know the height of a pole, for example, a street lamp, where you'll be able to find your height if you can measure your shadow. So what you would do is you would just say, okay, I've got a triangle 5 by 4, yeah, and I've got a smaller triangle made by Jake. I don't know his height, but I know that's his 1. And I know these are similar triangles. So the reducing scaling factor, because I'm looking at finding the side that is smaller compared to the taller one, is 1/4, yeah?
1 divided by 4.
Yeah. I'm not going to do anything yet. And now I want to find this height here, Jake height. So h is 1/4 times 5. And that is 1.25 meter. So Jake is a small boy, not very tall. But that makes sense. How tall is Jake? Give your answer to 3 significant figures. So nothing we could have done. The 3 significant figures are there. So we can just leave it like that. Okay. So that's how you would do this problem. And then you've got this one to do, a roof truss. Give your answer to 3 significant figures. And the last part is when we've got areas of similar shape. Because we've been looking at a length, but what comes often is an area. So if we've got a 2 by 2, we square, that'd be 4 square meters, for example. And if you draw a 4 by 4, so we've doubled each side. So imagine if the enlarging scaling factor would be 2, you get 4 by 4, but you can see the area went to 16. So now what we can tell is the second area is 4 times the first. So the scaling factor in 2D area is 2 to the power of 2 to get your 4. So every time you're going to find your scaling factor, if it's areas that you're trying to go from one area to a bigger area, the scaling factor needs to be squared. Okay? So scaling factor would be 2 square, which is 4. So let's have a look here. Work out the area of each shape and try to link area. So I've got a 4, 2, and a 12 and a 6. So the enlargement scaling factor here is 6 divided by 2, which is 3. So time by 3 both sides. But if you do 4 times 2, you get 8 square meters. Whereas if you do 12 times 6, you get 72 centimeters square. So now we said that the scaling factor was 3. But to go from 8 to 72, you need to time by 9. And 9 is just 3 times 3, so 3 square. Okay, so always remember, once you find your 1D, I would say, it's not 1D, it's like a length scaling factor, then the area scaling factor, you use that to square it to find your area scaling factor. The way to remember it is area is in centimeters square, so then that means you need to square the scaling factor. So you could have a question like this given, for example. We've got a couple of shapes that are similar, and the smaller shape is 42 centimeters square. If you make this one 4 centimeter instead of 3, what is the area of the larger shape? So the first thing first we will look for is to find the ESF, the enlargement scaling factor, 4 over 3. And now, so area is 42 times 4 over 3 square. So 4 over 3 square times 42, and that gives us 16 over 9 times 42, which is 74.67. So by going just 1 centimeter across, bigger, the area nearly doubled in size, which is 74.67. And if we were asked to give our answer with 3 significant factor, we would just round it to 1 decimal place, which is 74.7. Okay. So these are the past paper questions sometimes you've seen. Shapes A and B are similar. If shape A has an area of 5.2, calculate the area of shape B. Again, scaling factor, you would go for B, which is the, so you can just say area scaling factor. So area SF is 4 over 2 square, which is 2 square, which is 4. So if one of them is 5.2, the other one is going to be, so area of B, 4 times 5.2, which is 20.8 centimeters square, and not 10.4, like some people would just think, oh, it's doubled in size. So if you double the size, it's gone 4 times bigger. It's the same for this one. It's going to be 4 times bigger because we've doubled the size. 8 divided by 4 would be 2. 2 square, it's 4. 4 times 7, that would be 28. Again, similar type things. Enlargement of shape, you look for the enlargement scaling factor, and then you calculate. So this time we're going to go for a reducing scaling factor. So in this case here, we can just write area scaling factor is 24, because I'm going to the small one, divided by 36. Which is so that'd be 2/3 square of 4 over 9. Now to find P, it's just 4 divided by 9 times 45, And that is just 20 millimeters square. Okay. So we've got small boxes of chocolate. So this time we're going from what is the area of the fifth of the small box. So again, it's going to be reducing. Half as long. So you would say this is half. If this is 1, this is just half.
60.
Or if this is 2, this is 1. 1/2. Then you do 1/2 square for the area scaling factor. So remember what we've got is 1/2 divided by 1. Anything divided by 1 is just same number. And that's 1/4. So a quarter of 320, which is just 80. So small box area. And then you've got a couple of questions from Lecky book. Page 244 and 245. Okay. And what we'll do is, because it's getting quite late, next week, there's only 1 page left in the book to finish the similarity, but it'd be good to use it as a reminder of what we've done before, just to check. But instead of area, we'll do the volume similarity. So just think about it. If area, we went square, what's the unit for the volume? Yeah. So basically, you use the ESF or RSF, and then you just cube it. As simple as that. But we'll look at a couple of examples next week, just to remind you. Okay?
Yeah.
Because there's only not long left anyway. We'll be calling it a day. Yeah, so basically, you just do area. Yeah, so it's just a couple of questions. You can do them. Okay.
Okay.
And I think that's going to be us for today. I'm going to stop the recording.